Welcome back to this is lesson 4 where we're going to discuss Le Chatelier's principle and changes in temperature. So temperature, an increase in temperature will speed up any reaction, so it will speed up both the forward and the reverse reaction. But the endothermic reaction will be favored because it will try and remove the excess heat that was caused by increasing the temperature. Okay, so the endothermic reaction is favored by an increase in temperature because it will tend to decrease the temperature by absorbing the heat. We're going to look at example 1 on page 176. It's under the heading changing temperature. They are considering the reaction between hydrogen and iodine to make hydrogen iodide. Now, it says there, raising the temperature of the system will increase the kinetic energy of the molecules. So that means that the reaction will speed up. According to Le Chatelier, the reaction that will try to reduce or decrease the temperature will be favoured. Now, this reaction, the delta H for the forward reaction is negative, so it is the exothermic reaction. So an increase in temperature will favor the endothermic reaction. So if we look at a rate graph, where the system is in equilibrium already, and we increase the temperature, the endothermic reaction will be favored above the exothermic reaction. Both reactions will increase though. So the forward reaction, which is exothermic, increases a little bit, and the reverse reaction will increase in rate a lot. New equilibrium is established when the reaction rate of the reverse reaction decreases and the reaction rate of the forward reaction will increase. So this is the forward reaction. And that's the reverse reaction. Is favored. So what will happen to the concentration of the hydrogen? Because the reverse reaction is favored, that concentration will go up. What happens to the concentration of iodine? Because the reverse reaction is favored, that concentration goes up. What happens to the concentration of hydrogen iodide? Because the reverse reaction is favored, the concentration of hydrogen iodide will decrease. So another way to say this is that the equilibrium shifts to the left. As example 2 on page 177, I'm going to work through number 1.4. They say there, flask 1 contains an equilibrium mixture of nitrogen dioxide and dinitrogen tetraoxide, which is light brown in color. So it's a mixture of the brown gas, nitrogen dioxide, and the colorless gas, dinitrogen tetraoxide. The flask is placed first in hot water and then in ice. Decide which flask contains more nitrogen dioxide and which contains more dinitrogen tetraoxide, and then use the Chatelier's principle to explain the appearance of flask 2 and flask 3. Okay, so flask 2, they say, it looks like it's dark brown. Now, if we go to number 1, where 2NO2 is in equilibrium with N2O4, and they say that delta H is negative, the forward reaction is exothermic. So the forward reaction is exothermic. So if the increase in temperature caused more nitrogen dioxide to form, it means that the reverse reaction is favoured. But the reverse reaction, according to Le Chatelier's principle, increase in temperature will favour the endothermic reaction. So your concentration of dinitrogen tetraoxide decreases where the concentration of the brown nitrogen dioxide is increased. Right, then they go and they ask us to describe what happens in flask 3. Now the temperature there was dropped to 0 degrees, and you can see they symbolize it with less shading, so there is more of the colorless dinitrogen tetraoxide forming. So a decrease in temperature caused more dinitrogen tetraoxide to form. Therefore, the forward reaction is favored. Le Chatelier's principle says a decrease in temperature will favor the exothermic reaction. So your concentration of dinitrogen tetraoxide increases and your concentration of nitrogen dioxide decreases. Example 3 discusses the Haber-Bosch process. Now we know that the reaction between hydrogen and nitrogen to produce ammonia is exothermic. So an increase in temperature favors the endothermic reaction. So that is the reverse reaction. So your concentration of ammonia will decrease, your concentration of hydrogen will increase, and your concentration of nitrogen will increase. A decrease in temperature favors the exothermic reaction. And that is the forward reaction. So the concentration of ammonia will increase, the amount or the concentration of hydrogen will decrease, and the concentration of nitrogen will decrease as well. With the increase in temperature, we say that the equilibrium shifts to the left. Equilibrium shifts to the left, and with the decrease in temperature, equilibrium shifts to the right. So increasing temperature will speed up both reaction, but the endothermic reaction is speeding up more, trying to use that reaction, the heat, before it slows down to reach new equilibrium. The exothermic reaction will speed up to reach new equilibrium. Lastly, we look at the concentration. In this graph you can see that the endothermic reaction is favored with an increase in temperature. So the concentration of the hydrogen increases until it reaches new equilibrium. The concentration of the nitrogen increases until it reaches new equilibrium, and the concentration of the ammonia decreases until it reaches new equilibrium. Decreasing the temperature will slow down the reaction rates. So both forward and reverse reaction, the reverse reaction is slowed down more. That's why it drops more, and then it speeds up a little bit to reach new equilibrium. The concentration graph changes like this when the forward reaction is favored by decreasing the temperature. So you see the concentration of hydrogen and nitrogen drops, concentration of ammonia increases.